type of idea. This is really just one big problem. We're just going to figure out how do you graph something that is a rational function. And so we're going to start with our f of x equals x squared times x plus 4 times x minus 3 over x plus 1 squared times x minus 3. Okay, so the first question, which hopefully we'll start being a little bit more familiar with at this point, is how do we find the domain? So domain is all those inputs, all the things that we can put into it, all the x values that are allowed, so to speak. And so you want to think about three things that are going on. One, think of these as two individual equations. Okay, there's the top and there's the bottom. Are there any restrictions in the top or the bottom? Then think about it as a whole and know that, okay, what's my domain at the top? What's the domain at the bottom? And then I also know that I don't want the bottom to equal 0. So this should not equal 0 either. That's one of those restrictions. So if we think more basic, is there anything up top that I can't put in for x? Is there anything that gives me like an undefined or unreal answer? No. So I can put anything I want in on top. So that's all real numbers, so to speak. Anything that I can't do on the bottom. Well, there's not anything specific I can't do, because there's no square roots or anything, right? But when we think about that restriction piece, I don't want it to equal 0. So our x values we don't want would be -1 or 3. Good. So right away I know I can do all real numbers because everything fits into these functions except for the things that create the 0. So my domain is all real numbers. This is an acceptable way of showing it. All real numbers where, which is that vertical line, x is not equal to -1 or 3. Okay, the other way to do it in interval notation that a lot of us might be familiar with is the x is an interval from -infinity to -1 unioned with that -1 to 3 unioned with 3 to infinity. Okay, so there's two ways to do it. We've stressed that second one a lot, this typical interval notation, but this is also acceptable. You know, do all real numbers except for these two specific things. So where x is not equal to this. Okay, so that would also be a way you can show it. That's going to give you the answer to number 1 there. So what's the domain of the function? Okay, based on that, we know that there's two spots where x can't be something. So that should tell us something about is it continuous or discontinuous? Or in other words, as I graph this, will I have to pick my pencil off the paper? Yes. So this is a discontinuous function because the domain is restricted. So this will be our discontinuous. Okay. So those first two. The next thing that I personally like to look at next is there anything that cancels on top and bottom? Okay, because if there's anything on top and bottom that cancels, it basically kind of disappears from the function as a whole and creates a whole. Is there anything that we notice that might cancel out of this? So the x minus 3. So we're going to recognize right away that that x minus 3 cancels on top and bottom, so it's going to behave as if it was not there at all. And this is what our graph will actually look like. Okay, if we think back to chapter 2, where we had the piecewise functions, I actually gave you guys an equation like this, right? We had the x plus 2 times like an x minus 3 over an x minus 3. And we recognized that that part canceled. So it actually just behaved like x plus 2, so when you went to go graph it, you had this line of x plus 2, but there was a hole at x equals 3. So at 3, we saw we had this hole. And then I asked you what could you plug in to make that hole get plugged. And so you guys were like, oh yeah, well I know that 3 is what didn't work, so we'll plug that into this function. And so this coordinate point turned into 3, 5. And you're like, awesome. So if I plugged in 5 for y when x equals 3, I would actually plug that hole. Okay? So that's what we did in chapter 2. Similar to that, if we have a hole any other time, we can do it as well. So in this particular case, my hole occurs where? X equals 3. And so how can I figure out where this hole actually exists? We're going to plug it in. Okay. So my hole is going to be at the coordinate point 3, something. In order to figure out where that goes, we'll substitute 3 in for all of our x values. Okay. And so as we do that, we see we get 3 squared times 3 plus 4 divided by 3 plus 1, that quantity squared. So we end up with 9 times 7 over 16, or 4 squared. So we end up with 63 over 16. That becomes our y value. Okay? So there's where the hole is going to be, or roughly 3, 4. Okay? If we're thinking about it for the graphing purposes. Okay, so now you know exactly where the hole is. In this case, just the way the test is ordered, that's question number 8, just so you guys know. So question number 8 asks, does this graph contain any removable discontinuities? That's where you say, is there anything on top and bottom that would cancel? And you're like, yeah, there is. So that's where the hole will be created at that x equals 3, which we already knew was part of our domain restriction. And then we plug in that 3 to what's remaining to see what the rest of the graph would actually look like. And so we can find our specific hole. All right, so now we have a hole, we know the domain, and now we can kind of go back and look at some of the other stuff that we're hopefully more comfortable with from the last 3 weeks. And so I know that my graph is going to behave basically like this function, because I've already dealt with the hole. So the x minus 3 on top and bottom we've kind of already dealt with. So where are my x-intercepts? Find an x-intercept we want to. Plug in 0 for our y value. Good. So when we plug that in for the y value, we end up with 0. So we'll multiply by the bottom, which makes that disappear. And now we're just finding the zeros at the top. So my two x-intercepts are at -4 and 0. Anything special to note about either of those? Any of them has something multiplicity-wise? The 0 has a multiplicity of 2. So we know when we go to graph that, it'll bounce. Yes, Charles?
So since the x minus 3 is canceled on both sides, since the whole is not listed as an x-intercept?
It's not going to be an x-intercept, and it won't be a vertical asymptote. It's just going to be a hole there. So because it technically would be an intercept and an asymptote, it's that undefined moment.
Okay.
So it actually turns into just a hole, and we kind of ignore it. Okay? So then, that's why I like doing that piece first, so you don't list it as an x-intercept and then feel confused with it later. So then with a y-intercept, how do we find y-intercepts? Plug in 0 for our x's, good. In this case, we end up with 0 times stuff over stuff, so we end up with 0, which hopefully we were expecting since one of the x-intercepts was 0. So we'll also have a y-intercept there. And then, so that's questions number 3 and 4. Now we're going to get into the end behavior stuff. And this is where it's a little bit different than what we've done with horizontal asymptotes. I will give you some that still have horizontal asymptotes to practice with. Okay? But we're going to look at those extremes again. So as x approaches infinity, so as x gets really big, what is y doing? So x approaches infinity, y approaches what? In this case, if we multiply it out, we'd end up with an x cubed plus 4x squared over x squared plus 2x plus 1. So as these get really big, we can kind of ignore the smaller pieces, and that kind of goes away. So we end up with an x cubed over x squared. What do we start to approach? We start to approach infinity. Why? Because it's basically just approaching x. We're approaching this straight line x. Now we can go figure out exactly what we're approaching, but we know we're kind of going towards infinity. I can use long division. Here's where long division is going to come back into the game. If I were to take x cubed plus 4x squared and do long division on it, I can figure out exactly what my slant asymptote is going to look like. Okay, so in this particular case, x squared goes into x cubed x amount of times. And then I can take that x and we're going to multiply it by that front piece to see what's left over. So we end up with x cubed plus 2x squared plus x, and then we'll subtract it. So we'll end up with 0, and then 4 minus 2 gives us 2x squared, and 0 minus x is minus x. Then we repeat that step. Does x squared go into 2x squared? Yes, it goes in there 2 times. So this will be a plus 2. And then we'll do the same thing. Multiply the 2 by the circle here, and then we'll end up with 2x squared plus 4x plus 2. We'll subtract it. We'll end up with 0, negative 5x, minus 2. Okay? And then we can repeat that step again. Does x squared go into negative 5x? No, it does not. So at that point, we're done. That becomes a remainder, okay, which you can actually use the remainder to go figure out where you cross your slant asymptote. We're not going to focus a lot on that right now, but that's how you would know where it crosses. But the important part is we just found out that our asymptote is at the equation y equals x plus 2. Okay, so now we have this slant asymptote instead of a horizontal one. Okay, and it actually works very similar to what you've seen in the past. So let's pretend real quick, just so we get back into a familiar place. We had an x cubed plus a bunch of stuff divided by an x cubed plus a bunch of stuff. Okay? What am I approaching as I get towards the extremes? 1. And we could see that with long division, because you would have x cubed plus all of its stuff, and then x cubed and whatever. And we just look at that lead term. How many times does x cubed go into x cubed? And you'd say it happens 1 time. And so I'm approaching the line y equals 1. Okay? Does that kind of make sense and hopefully bring a little bit of familiarity back to it? So we can use long division every single time to find your asymptote, whether it's a slant one or a parabola or anything else crazy, or as basic as just a horizontal line. All right, so this should get us the answers to number 6. Does this contain a slant asymptote? The answer would be yes. The way you know instantly is the top degree is greater than the bottom degree. Okay? But when we do that long division, it'll give you this linear quotient piece. And so you'll be able to see that, yeah, that's actually just a slant line. We have a slant asymptote. Okay? If they're the same degree, so like we've seen in the past, like on the final, then you approach a horizontal line. And if the bottom is greater, so let's say this was x squared over x cubed, you would approach 1 over x, which is going to make things really, really small, so we're approaching 0. Okay? So there's 2 times where you'd end up with horizontal asymptotes, and then there's 1 time where you'd end up with these slant ones. Yes?
So would the slant asymptote equation be negative 5x over x squared plus 2x?
No, just y equals x plus 2. Correct. So the remainder piece is going to tell us where do I cross that line. And we can plug that in and worry about that a little bit later. But I want us to get the large picture stuff first. The big piece is here is the actual asymptote. Okay? So we know where x is. If x is approaching infinity, y approaches positive infinity. What happens if we head towards negative infinity, the extreme, the other direction? What is y going to approach? Negative infinity. Good. So that hopefully makes sense, because as we continue across this asymptote, this goes towards positive infinity, so will y. As x goes towards negative infinity, so will y. It's just going to follow that linear path. Okay? So now we have 5 and 6 complete. The last piece, which hopefully we're still kind of familiar with, is finding the vertical asymptotes, which actually I'm going to do on that last page because we've got something up there. How do we find our vertical asymptotes? Zeros for the bottom. So in this case, x is going to equal -1. So that's going to give us the one vertical asymptote we have. Okay, anything to note about that particular asymptote? How is it going to behave on either side of it? Are they going to be together, up, or down, or is it going to be one of each? It's going to either be up, or down, because it has that multiplicity of 2. So something to note for our graph, we're going to have that multiplicity of 2. So it'll either look like that volcano or the valley type look. Okay? So this should help us fill out 1 through 8. Now we're going to be able to take all those pieces and tie it back together and build our graph. So from the beginning, we know the domain. We know that it's discontinuous. We know we have x-intercepts at -4 and 0. 0 has multiplicity of 2, so we're going to bounce at that location. Our y-intercept we've identified as 0 as well. Our end behavior we recognize is going to be down and up. We have a slant asymptote. At the equation y equals x plus 2.
Is the end behavior up, or like we use originally didn't say it was down, we said it was up, or down.
Oh, sorry, that was for the on the either side of your vertical asymptote. That was so on my vertical asymptote for x equals -1. On either side of this asymptote, this thing will look up, or down. So what I mean by that is if I had a graph that had these asymptotes, it's either going to look like that, and that's because the multiplicity of 2 here, which we see from the x plus 1 squared, tells me that I'm going to bounce basically off that like infinity ceiling. So very similar, like we bounce at x-intercepts with multiplicity of evens. Multiplicity of even here, we're going to have that same bounce effect, so to speak. So the true end behaviors of the function, that was the as x approaches infinity, y approaches infinity. That's this up part. And then as x approaches negative infinity, y approaches negative infinity. That's the down part. Did I just make that super confusing, brother?
We just put the original
So,
like on the graph.
yeah, I'm gonna actually draw the graph here in a second. Okay. So you've got your vertical asymptote, and then the last piece we needed was the hole, which we identified the hole at 3, 63 over 16, right? So these are all the pieces that we just solved for. And now we can build the graph. So as we're building our graph, for the most part, just kind of ignore the y scale. We're just going to look at the x values for the most part and kind of get a general picture. So you know you have, excuse me, you know you've got the vertical asymptote at -1. You have a slant asymptote at x plus 2. We graph that the exact same way you would graph just the line x plus 2. So you got a y-intercept of 2 and a slope of positive 1. So we're going to have something that looks kind of like that. There's your 4 sections, so to speak. Okay, but it's with a slant instead of a horizontal line this time. And then let's go plant the points we actually know. So we have a intercept at -4. We have an intercept at 0. And we have a hole that we know we're going to approach, but it's just going to be that open hole at 3, 4, roughly. So there's going to be a hole somewhere around there. Okay? So how can I piece all this together now to make the picture? Well, I know it's going to bounce at the 0, 0 because of our multiplicity of 2. So do we think it's going to bounce that direction or bounce downwards, and why? What am I going to eventually approach? Charles.
Because your behavior is down. So on that side of the asymptote,
Good. So eventually I know I want to be approaching that asymptote, that extreme there. So this is going to go through our hole, and then it's going to bounce at that x-intercept, bouncing up. So we end up with something kind of like that. And then here's that piece where the tails at the asymptote are going to be together because we have the multiplicity of 2. So this is going to be together. We'll come from there. And then eventually we'll know we want to approach that asymptote again down there. And do I go through or bounce at this one? Through this intercept. Multiplicity of 1, so we're going to go through this one. So we end up with a graph that looks something like that. Roughly. Yes, Charles.
So how do you know you want to do the slant asymptote?
Because I had to. There's no way that I can cross a vertical asymptote because it's an undefined event. I know that the only places I can cross the x-axis are at the 2 intercepts. This one I knew I had to bounce at.
Yeah.
So this is going to force me to go up. The other way you would know exactly where it crosses is if you took that remainder and plugged it in for y and then solved. But that'll take a little bit more complicated math. Okay? All right, so this is ultimately what we're going to try to be able to do. Hopefully questions 1, 2, 3, 4, and 7 are familiar to us. Okay, those are things we've done the last 3 weeks, so hopefully that helps us out.